Hello students, I am Atiqur Rahman. I teaches at the Department of Geography, Jamia Millia Islamia, New Delhi. Today we are going to discuss about the basic physics of remote sensing. In this module, we are going to discuss various objectives, and to understand the remote sensing, we need to understand the science behind it, the physics behind it, because behind this remote sensing we have optics of light. The energy what we use is the sun's energy in the optical remote sensing. There are different remote sensing that we will talk later in the different modules. So, in this module we are going to talk about basically the physics of remote sensing. When I say the physics of remote sensing, that covers entirely the energy that is being used and captured by the different objects which are there on the surface of the earth. So, in this, the learning objective of this basic physics of remote sensing covers emittance, radiation, existence, physics of Kirchhoff Law, Stephen-Boltzmann's constant, and there are different other laws that will be covered in this objective. So, what we have in this physics of remote sensing, precisely it uses the sun's energy, as I said before. Sun's energy, that means any object at absolute zero, at the energy above absolute zero, radiates electromagnetic energy that we call is the electromagnetic radiation by the virtue of atomic and molecular vibrations. So, what we have in this, we are going to discuss, we are going to understand, we are going to see how this energy, sun's energy, is going to be used by different sensors that have been designed the various by the physicists, the scientists. So, when we say the sensors, it is nothing but is a optical mechanical device that captures the energy which is being reflected back from the surface of the earth. On the surface of the earth, what all we have different objects. There are two types of objects. One is the human objects, human features, and second is the natural features, and all these features keeps on changing with the passage of time. So, natural features that changes less frequently, but the human features, human objects that keep on changing at a faster pace. So, in the physics of remote sensing, we try to see what are different science on which the sensors and the technology that uses and acquires the energy which is being reflected back from the earth's surface back to the sensor, and that energy gets quantified into digital number, and that number get converted into satellite data, and that we get for the common use. So, basically in this we are trying to see what are different laws, what are different interaction of energy with the different objects, and what is science precisely behind it. So, that is a basic learning objective of this module in the basic physics of remote sensing. We will see little later how that I can explain you by the different diagrams, because if I explain you straight away, that will not be easy to understand, but it will be better to understand by showing you different diagrams, how the energy comes, how the energy interacts with the atmosphere, how the energy interacts with the surface feature on the earth, and how it goes back, and in this process how the energy is being quantified. So, what we see that energy, sun's energy, we all know that is releases energy in all the direction in equal amount all the time, day and night. If we see, there are different temperature at the suns, at the inner surface, at the middle surface of the sun, and the outer surface of the sun, that we call the photosphere. At the photosphere, the sun's energy that radiates by the conversion of hydrogen to helium, that is at about 6000 degree Kelvin, 5777 degree Kelvin, that travels in all the direction and that reaches the surface of the earth. Before reaching the surface of the earth, it interacts with the earth atmosphere, and then it reaches the surface of the earth. When it strikes the surface of the earth, the sun's energy, what happens? Three things happens. Energy gets reflected back immediately, that is not being absorbed. Rest of the energy is being absorbed at the surface of the earth, and after absorption what happens? It slowly emits, because as per the law of thermodynamics, energy cannot be stored, its energy cannot be destroyed, but it can be transformed from one form to another form. The sun's energy which comes from the sun and reaches the surface of the earth, that is in the form of short wavelength, because the energy is hot. So, hotter the body, shorter the wavelength, but once it goes back from the surface of the earth to the atmosphere, it is in the form of long wave. So, the energy which reflects back from the surface of the earth goes in the form of long wave radiation and reaches the sensor, which are placed at altitude of about 600 kilometers to 750 kilometers, and that energy get recorded and that get converted into digital number. That we will talk in another module about the interaction of energy with the atmosphere and earth. But here in this module, we are precisely talking about purely the physics of remote sensing, what all science, what all the laws that is being applied in this remote sensing, the science of remote sensing. As I mentioned before, the Kirchhoff Law, the Stephen-Boltzmann constant laws and different other laws. So, we will talk one by one. So, in order to understand the physics of remote sensing in a better way, let us understand it through the figures and diagrams. So, let us go to the blackboard. So, the very first issue is that of, I was telling you, the electromagnetic radiation. The energy which is travelling from the sun reaches the surface of the earth and hit the target, as I told you, that human as well as the natural feature. So, what happens if we see here, suppose this is the sun, the energy travels in all the direction, right. So, what happens if the energy is travelling through a wavy fashion? So, that we have a simple formula to calculate the energy, C is equal to nu lambda. What we have, if I try to let you understand through my fingers, this is the source of light energy, that is this sun's energy which is travelling, that is the speed of the light. This is the electrical field and this is the magnetic field. So, what we have, that the sun's energy which is travelling in a wavy fashion like this. So, from one crest to another crest, this distance is called lambda. So, if you have one situation like this, another will be like this. Here what we see, that lambda is large. So, this is energy which is in the form of long wave radiation, whereas this lambda, where the distance is short, that is called as a short wave radiation. That means the sun's energy which comes to the surface of the earth, that is in the form of short wave radiation. Whereas, when it strikes the surface of the earth and it goes back in the form of reflectance, that is in a long wave radiation, and with a simple formula, simple understanding, that hotter the body, shorter the wavelength, cooler the body, longer the wavelength radiation. So, as I told you that sun's energy, which is the source here, suppose this is the sun energy here, it travels, and that is the speed of light, that we call is a c, and if you see vertically up, that is electrical field, and if you see this side is a magnetic field. So, what we have is the sun's energy which travels in a form of wave like this, and from one node to another node we call is a wavelength, that is a lambda. If energy is hot, this lambda, distance bit of this lambda will be less, but the energy is low, what will happen? The energy, this distance of the lambda will be long. So, to calculate this speed of light, we have a very simple formula that we call is a c is equal to nu lambda, whereas c is the speed of light, that is 3 into 10 to the power 10 meter per second. Now, to understand the sun's energy which comes to the surface of the earth, it comes through different spectrum. There is natural existing spectrum, that is called electromagnetic spectrum, EMS. So, it is naturally existing spectrum which nature has created. So, we want to see how much energy is coming in a particular spectrum. So, if I tell you in general that about 40% of the sun's energy which comes to the surface of the earth is in the form of in the region that is called a visible region, and the region in the spectrum which we have is 0.4 to 0.7 micrometer. So, we want to see how much energy is coming in which region. So, 40% of total sun's energy comes in the visible region, remaining 50% of energy comes under the infrared region, and about 9% of energy comes under the ultraviolet, and about remaining 1% under the rest of the energy. Now, if you see, if I draw a spectrum to understand you in a better way, suppose this is the electromagnetic spectrum that we call is EMS. This is the visible region. If we go left side of it, we have the X-rays, gammas and other rays, that we have the short wave region, and if you go right side of it, we have the long wave region, that we have the infrared, IR, then we have the thermal, then we have the microwave, and so and so. So, if you see the figure 1, what it shows? It shows the principal division of electromagnetic spectrum, and in figure 1 you clearly see on the left side the crest is very close by. If you see in the figure 1, the crest is something like this, very close by. If you go right, the crest becomes, the distance increases, that is the distance of the lambda increases. So, therefore, I precisely said this is a short wave region and this is a long wave region, is starting with the visible, and you can see in the figure 1 that there is a principal division of visible region. This visible region is further divided into blue, green and red. Blue extends from 0.4 to 0.5 micrometer, green extends from 0.5 to 0.6 micrometer, and red extends from 0.6 to 0.7 micrometer. Better you can understand and see in the figure 1. Now, another learning objective is to understand electromagnetic radiation quantities, and the very first is called the radiant energy. In a very simple way, radiant energy can be defined as the energy carried by electromagnetic radiation. The radiant energy causes the detector element at a sensor to respond electromagnetic radiation. Number 2, that is the radiant flux. Radiant flux is defined as the total power of radiation emitted by source, that is the sun, it could be lamp or any object. The third issue is the irradiance. Now, we simply define irradiance as the radiant flux intercepted by a plane surface per unit area. It could be 1 square kilometer, it could be 1 square meter or anything. So, what does it mean? That the total sun's energy, when it reaches the surface of the earth, in a per square using unit area, what is the energy that is being intercepted? That is called the interception. And the unit of the irradiance is watt per square meter. Now, another issue is the excitance, that is emittance. Emittance is defined as a radiant flux leaving a surface per unit area of the surface. The flux may leave a surface or it may leave in all the direction within a hemisphere or a surface, and it is denoted by M, that is clearly shown in figure 5. Now, another issue is that of solid angle. Solid angle can be defined, it is a cone angle subtended by the proportion of the spherical surface at the center of the sphere as shown in figure 6. Now, radiant intensity of a point source is given a direction in the radiant flux per unit solid angle of the source in that direction. That means the energy which is living in a particular direction through the cone angle, that is called the radiant intensity. Unit of radiant intensity is watt per steradian as shown in figure 7. Now, another issue under the heading that is we call is the physics of remote sensing is the radiance, is defined by the radiant flux per unit solid angle leaving an extended source. If you see the solid angle cone, if you go away, that is the extended portion which is living. So, that is the extended source in a given direction per unit projected area of the source in that direction, that can be clearly seen in the figure 8. So, friends, what all I have explained you before in short, that is radiant energy, radiant flux, radiant intensity, irradiance, radiant emittance and radiance, that can be clearly shown through diagram in figure 9, which makes you a comparative understanding and comparative analysis of the terminology that is being used in the physics of remote sensing. Now, another issue under this e-learning module is Lombardian surface, which is the plane source or the surface for which radiance L does not change as a function of angle of the view is called Lombardian, which is known as perfectly diffuse surface. For a Lombardian surface, what we have existence m is mu into radiance L. Now, second issue under this is the spectral quantities. The spectral quantities, that is spectral electromagnetic radiation, that is the electromagnetic spectrum, consists of continuous frequencies or the wavelength of each of which carry a share of total radiant flux. Now, the energy which travels from the sun reaches the surface of the earth, as I told you, through that crosses the atmosphere and then it reaches the surface of the earth. So, in that process there are other phenomena that takes place. One is called hemispheric reflectance, transmittance and absorptance. Now, to understand the hemispheric reflectance, which is defined by the ratio of reflected existence of the plane to irradiance on the plane, it can be expressed as rho is equal to reflected energy m upon irradiance E. The hemispheric reflectance, that is a tau, is defined as a ratio of transmitted energy leaving the opposite side of the plane. It can be represented as tau is equal to transmitted m upon irradiance E. And the third is hemispheric absorptance, that is alpha, which can be denoted as a fraction of incident energy which is absorbed by the energy, is given as a formula alpha is equal to 1 minus tau minus rho. For a perfect black body, reflectance, transmittance are 0 and absorptance is unity, that is 1. Whereas for perfect white body, absorptance and transmittance are 0 and reflectance is unity. But in reality there is no perfect black body, there is no perfect white body. That means there is something in between perfect white and perfect black, and that we call is the grey bodies. Now, let us understand another issue under the physics of remote sensing is the thermal emission of radiation. Now, all objects at all temperature emit electromagnetic radiation at all wavelength, as I said in the beginning of my lecture. The thermal emission of radiation is due to the conversion of heat energy, which is kinetic energy of the random motion of the particles of the matter into electromagnetic energy. Thermal emission of radiation depends on two parameters. One is absolute temperature and second is the emissivity. The total thermal radiation from a body increases with the force power of temperature, that is T. The absolute temperature is given by T is equal to 273. Temperature in degree centigrade is the unit of degree Kelvin. The emissivity factor is the characteristics of the material, a measure of its capability to emit radiation due to thermal energy conversion. The energy of a body depends upon the absorptivity ability. It is the fact that the good observer or the good observer are the bad reflector and the bad observer are the good reflector. Now, let us understand the radiation principle. Before discussing various radiation principles, let us understand the radiation in the context of remote sensing. Basically, it is the energy that comes from the sun, as I said before, as mentioned above, that it travels through some material or through space. There are mainly three types of radiation, that is light, heat and sound. Now, to understand this, let us understand Planck's law. Planck's law of a body radiation predicts the spectral intensity of electromagnetic radiation at all wavelengths from a black body at a given temperature T. The spectral existence m for a black body can be calculated by using Planck's law. That is, m is equal to Ci minus 5 exponential 2 C2 upon T minus 1 into and the minus 1, where C1 and C2 are constant, that is a wavelength, and T is the absolute temperature. We all know that spectral existence of a body is not the same at all wavelength, and the spectral existence is low both at short and long wavelength region. Now let us understand this same through this figure. What we have on the left side, we have the short wave region 0.1, 0.2, 0.3, 0.4, 0.5 micrometer, and if you go right side, we have the larger wavelength region. Now what we see here is that on the short wave region, the spectral radiance, that is existence, is high, and it increases with the increasing wavelength region, but its wavelength is spectral radiance reaches maximum somewhere in between 0.4 to 0.7 micrometer, and as we go right side on the longer wavelength region, the spectral radiation reduces. Now another law that is important to understand, that is Stephen-Boltzmann law. It states that the total radiation emitted by a black body in the entire electromagnetic spectrum is obtained by integrating the area under Planck's distribution curve, which is directly proportional to the 4 power of the absolute temperature, that is m absolute black body is equal to rho T to the 4. Another issue is the spectral emissivity, which is also very important in a remote sensing data acquisition, which states that there are 3 basic radiation law as described earlier holds good of the black body. All other substances are characterized by the spectral emissivity, which can be defined as a ratio of spectral existence of a material to spectral existence of a black body at the same temperature is expressed as follows. The lambda is equal to A, that is the material of a body of object degree Kelvin upon material lambda, or that is a black body, that is in the form of degree Kelvin. If you know the spectral emissivity of a black body is spectral existence, total existence, and the wavelength of the Planck peak emission can be easily determined. Now let us understand the Kirchhoff law. In order to understand the emissivity, we need to know the Kirchhoff law. The law states that the spectral emissivity of the material is equal to the spectral absorptivity, that is lambda. E lambda is equal to phi lambda. It means that if a black body is capable of emitting certain radiation, it will absorb that radiation when exposed to it. The value of emissivity E varies between 0 to 1, which depends on the dielectric constant of the material, its temperature, wavelength, and the surface roughness. For a clear water, emissivity is between 0.98 to 0.99, that is very high spectral emissivity. Healthy vegetation, green cover, which has spectral emissivity between 0.96 to 0.99, wet solid is 0.95 to 0.98, and dry vegetation 0.88 to 0.95. The emissivity is characterized by material can be summarized as follows. For a black body, emissivity will be unit, that is 1 at all wavelength. For a grey body, it is less than equal to 1. For imperfect black body, that is perfect reflector, emissivity will be 0, whereas all other body emissivity is a function of wavelength. So friends, today I have tried to demonstrate, to teach you about the basic physics of remote sensing, where we have discussed different laws, different characteristics of energy, sun's energy which travels. We have talked about radiance, we have talked about irradiance, we have talked about different laws, physics of laws, Planck's law, Kirchhoff law, Stephen-Boltzmann constant. These are very important in order to understand the remote sensing. Although as a student of geography, as a student of geology, or as a planner, when you are dealing with the remote sensing satellite data, we do not need to know exactly understand these laws. We do not need to mug up these laws and these things, but at least you should know what all is this, what are the science behind this, that is very important. So therefore, based on those objectives, based on those issues, I was trying to understand, trying to let you these laws. So these laws, I hope that with reading these module, you will get to know an idea and the glimpse. Although you are may not be the student of physics, you may not be a student of other science, you may be a student of maybe humanities, languages, or any other social sciences, but you should have clearly got some of the exposure, some of the understanding what all it is, how it functions, how it operates, and how this energy, the sun's energy, is being used and applied in the science of remote sensing, which is very important. So, I do hope that you may have got some insight through this lecture, and you can keep on reading the module which is there on the website of UGC, that will give you more clear and detailed understanding. Thank you very much for your patience.